So now we will actually look at problem formulation for solving systems. So formulation, oh, again the same problem. So what I mean by formulation is we will give some examples where linear systems arise that actually solve a problem at hand. And we will do two examples. One will be actually sort of a networked loop of reactors, which is common in chemical engineering. Okay? So those are typically, they're called network flow problems. So I have networked system, okay? And those networked systems, typically when I'm actually solving a problem in them, like flow through the entire network, for instance. And it could be flow, as in flow of a fluid, but it could be really any type of transport through that network. So transport in networks, which is omnipresent everywhere, we can think about it as pipelines, okay? Those pipelines could be from the size of the building to some network of reactors in a lab to actually pipelines, gas pipelines, you know, on a state level. So I can have a range of networks of that type. But I could also have networks of resistors and so forth in electrical engineering. Okay, same thing. Those are our motherboards in the computer. So there's all kinds of things that we actually typically look at as transport in networks. Traffic is another network. Okay, it's a network of roads, and you actually have flux of cars, which is sort of fluid. Okay, you can look at car density, right? Average density of the cars on the road, and it actually is modeled as fluids. Okay? So in that sense, there's a lot of places where we can actually look at networks. Okay? So that's going to be an example of these networks. And the second one will actually come from differential equations. So a lot of times when we're actually discretizing differential equations, so by that we're looking for numerical solution to the differential equations that you are right now dealing with analytically, and you're looking for formulaic solutions. Well, those exist only for a certain class of equations. For most of them, we actually have to resort to numerical methods. In those cases, we often actually, as a derived problem from discretizing this equation on some domain, we actually get to solve a linear system. So those are the examples we're going to go with. So let's, without further ado, start with 3 reactors. Okay, so I have reactors. Okay, and I'm gonna unimaginatively call them 1, 2, and 3. Actually, this one is 2. And this one is 3. And they're actually connected. So there are basically literally tubes going from one to the other. And these are the tubes that exist. So there is this one. And there's flux, volumetric flux Q13 from 1 to 3. Going in here. Then there is flux from 1 to 2, Q12. Then there is from 2, we have Q23. And from 2, we also have Q21. And I have major 1 line feeding into the system, and that one is feeding into reactor 1, and I know that there's 100 meter cube per second. So flux is typically volumetric flux, as in certain volume per second.
Is there not a form between 3 and
3 to 2, no. But 3 is getting a separate line of some chemical, whatever chemical that might be. That is 20 meter cube per second. And then there's flux going out called Q33. So we want to figure out what are these fluxes in between at steady state. What does steady state mean? It's constant in time, okay? So basically each of these lines, so initially if I just start the system, when I just start the pumps moving and anything, I'm gonna have a ramping up to whatever my pump can deliver and go through the first pipe, and then you have to establish flow through all the other pipes. You probably need to push some air out too, but that's a whole separate discussion. Okay? So it takes a moment to establish what we would call steady state flow that doesn't change in time. So we want to solve for that. So when there's no change in time, then one thing that I can apply to actually solve the problem is general mass balance. Basically, whatever comes into my system has to be the same as what comes out because there is no change in accumulation. Or it's equivalent to some accumulation that I know and can track, right? But in this case, I have no accumulating point or no sink other than those things that are going out of the system, like Q33. Okay? So basically, whatever comes in has to come out. So what can you tell me immediately about Q33? That is my only line out of this system. 100 plus 20. Okay, so I have two lines feeding in, okay, and one coming out. So general mass balance. So we need steady state for this. So to get the steady state fluxes, we apply mass balance. Okay? Mass balance is our key principle. And mass balance means what comes in per second has to be what comes out per second. As we have no sink or accumulation point. Within this system. Okay? Therefore, just the general mass balance tells me that 100 plus 20 meter cube per second has to be equal to Q33. So this is really not an unknown. I can just treat it as something I know. Now this is the mass balance for the entire system, because other than two inlets and one outlet, the rest of the sides are closed. But I can also apply mass balance for each component or subcomponent of the system. Okay? And I have three reactors as three subcomponents. So whatever comes into reactor one has to be equal to what comes out. So that will give me three equations, okay, for these fluxes. And those are the equations we're going to solve. Okay? So mass balance also applies for each reactor. And that will give me, I will get three equations. Okay? So in reactor 1, so basically my reactor 1 we have that whatever comes in is 100, and what else comes in? Q21. It's actually 21. We don't have a Q22. And what comes out is Q12 and Q13. So I'm just going to order them. These are Qs. These funny eggs with little tails are Qs. My handwriting is not the best. That's the understatement of the year. Okay. Now, what about my number 2? Number 2 says that what comes in, which one comes in? This one over here. So Q12, what comes up? Q21 and Q23. And then 3 says that what comes in, which is Q13 plus Q23 plus 20, has to be equal 120. I already solved what Q33 is, right? Is everybody cool with this? We can do this with reactors, we can do this with lakes and rivers, we can do this with any kind of networked anything, okay? As long as I have reasonable way to delineate what is this part 1. So reactor is easy because I built it. Now delineating what all comes into a lake is not so easy, okay? But my lake takes contributors from all of the rivers and streams that go into it, right? So that would be another network that I could look at. Okay, so this is it. This is our system of equations. Now, how many unknowns do I have? Let's go with the ordering. We can call them something that we are more familiar with. Let's call this one x1. So I'm going to order them in order. So Q12 will be x1. Q23 will be x2. Then Q21 will be x3. So this is my, I'm kind of thinking about them as a matrix, and I'm just going down the rows and numbering them that way. So this is x3. Q23 I have not had so far, so this is my x4, and this is my x2 and x4. So this is just labeling them the way we're a little more used to labeling things. Okay? So then what I actually have when I put all of the things that I know or don't know on the left side and everything that I know on the right side, right? Then my first equation is minus x1 minus x2 plus x3 is equal to minus 100. Is that correct? Again, unknowns on the left, known stuff on the right. And then x1 minus x3 plus minus x4 is equal to 0. And x2 plus x4 is equal to 100. So I have 4 unknowns and I have 3 equations. Okay? So how many solutions at best will I have? In the best case that I actually have some solutions, there will be infinitely many because I don't have the system that is fully determined, which is a good thing. Imagine a situation where you kind of have to hit precisely given fluxes, one of them 53, one of them 100, in all of these pipes, okay, in order to flow. Oh my. This way, when it has infinitely many solutions, meaning it's like, okay, if in one of these pipes I have flux x1, the others will sort themselves out accordingly depending on that x1. And that's actually a good thing, okay? Does everybody see that? So you don't want a unique solution in this type of a system because you want to be able to flow for multiple ways. Okay, so let's actually go and solve. Now, again, this is my problem formulated. I'm going to solve it because we don't solve many cases with infinitely many solutions. Okay. So I could go through Gaussian elimination. That's fine, but here it's actually kind of easier to eyeball things. So I can immediately choose to just look at the first one and the second one and look at things. So we have x1, so if I have the last one, for instance, it says that x4, okay. So I'm going to write down. So we will have infinitely many solutions since number of equations is less than number of unknowns. So you can pick, so some of these x1s, x2s will be expressed in terms of the others. You can pick what you want to do if you're solving just by hand. So for instance, let's say that we are targeting that my x3 and x4, or x4 is my first parameter, so then my last equation says that x2 is 100 minus x4. So this x4 I treat as a free parameter. And then I'm going to plug in this x2 into other equations. So I'm going to have from my first one, I'm going to have that minus x1 minus x2. So that's 100 minus x4 plus x3 is equal to minus 100. So based on this goes away. Minus x1 is equal to minus x4 minus x3. So my x1 is simply x3 plus x4. And my second equation actually says the same because it's x1 minus x3 minus x4 is equal to 0. So that also says x1 is x3 plus x4. What does that mean? out of the 3 equations we thought we had, only 2 are independent. Okay? Remember that the discussion at the very beginning we had on independent versus dependent equation? So one of these equations, one of the 3, is simply a linear combination of the others. So this is basically the same as 2. So we have only 2 equations are independent. So basically my solution is pretty much that x2 is 100 minus x4, and my x1 is x3 plus x4. So my x3 and x4 are so-called free parameters that I can choose any way I want, and the others sort themselves out. Now normally, the way I drew the problem, I'm thinking of these fluxes as being positive because they have a direction. But if one of them is negative, that just means that whatever direction I assumed on the graph is actually reversed. Okay? So I can accommodate all kinds of flows in there, really, in terms of who's flowing where. That's it. That is the solution. Okay? Now let's actually discretize a differential equation. I heard differential equations are your favorite part of your undergraduate education so far. Is that correct? Well, I guess it depends on the professor, eh? Okay. I actually have no clue who is teaching it, have no information on that. But we're going to actually look at the heated rod. So I assume I have a wall and then a rod between that wall and another. And I'm keeping this wall at temperature T0, which is 40 degrees. And I'm keeping this wall at temperature, I'm going to call it T5 in a moment for a reason. So I'm going to call it 2. And that one is 200 degrees. And the distance between them is 10 meters. So I'm going to say, oh, this is x0 is my at 0 meters, and x5 is my 10 meters. If my rod was completely in some sort of insulator, okay, so it was not losing any energy to the ambient air, okay, then I would actually establish just a linear temperature profile between this 40 degrees and 200 degrees, right? But that's not the case. I actually have air, and there is some heat transfer between the rod itself and the air, right? So I know if I have any piece of hot metal here in the air, it's going to actually give out some of that heat. So we're wondering, well, okay, how different is this temperature profile? And the way that is modeled, I'm not going to go into deriving this differential equation, but the way it's modeled is that we have a differential equation for this heat, or for temperature profile, and that is d squared t dx squared, so second order derivative, plus h, which is a transfer coefficient, Ta, which is my ambient air temperature, and that is 20 Celsius degrees, air, minus temperature at the rod is equal to 0. So basically this part, h, Ta minus T, my loss, or the temperature equilibration with the ambient air, is proportional to the difference between my temperature at a point and the ambient air. Okay? So typically heat transfer or heat flux is always proportional to delta T, or gradient in temperature, delta T over the distance, right? So here I'm just saying like overall loss is proportional to the temperature difference. It always is. Okay? So if I have hotter versus colder, the bigger the difference, the faster the transfer will happen. And H is basically what tells me something about air and, I'm assuming this is a metal rod, air-metal contact, and how fast the transfer between the two happens. I know that air is relatively low conductivity for heat, 100 times lower than a metal, and therefore they can't catch up with each other, so they can support different temperatures, right? Otherwise, the temperature would very quickly become very continuous, and I would not have a clear difference between the metal and so that's just the physical behavior when I have two things that don't have transport coefficients that are comparable scale. So have you done transport phenomena? Okay, so no? Okay, so we will know much more about this when the transport hits. Okay. So this is heat transport. Okay, but again, it should be something that is intuitive, right? I know that my metal next to air can be much hotter, so it can support this temperature jump, and there's the transfer between the two depends on the size of that jump. Alrighty. So this heat coefficient, this H is actually given, and it's 0.0 meter to the minus 2. And we are wondering, well, what is my T? Is T of X? What is it? Now, this is something I can solve as a differential equation. I will pretend I don't know how to do that. This is numerical class. So I'm going to approach this as a numerical problem. Okay? And as a numerical problem, this is how we approach it. So what I want to do is I want to find out temperatures along this rod. So I'm going to call what I say, discretize my domain. And I will find a finite set of points along this rod where I'm going to look for solution. And not in between, just at a finite set of points. This is what numerical solutions do. That set of points could be really close to each other. I could do this really finely, okay? But it's still a finite set of points I'm solving at. I'm not solving at a continuous, because it's impossible to do in a computer, okay? Computer always works with finite stuff. So I'm just going to identify 4 points in between the existing ones. So this is my x1, x2, x3, x4 in terms of how far it is from the end of the rod. So I have x0 is 0, x1, x2, x3, x4, and my x5 is 10 meters. And my temperatures at those points are T1, T2, T3, T4. So I am looking for T1, T2, T3, T4. That's it, those 4. Okay? Okay? And the spacing in between these points, I don't have a reason to do it some variable spacing, so I'm just going to do equal spacing. So what is my spacing? These 4 points divide my rod into how many segments? 5. The total length is 10, therefore each segment is 2 meters, yes. So maybe I'm going to call this delta x is 2 meters. And I have the same delta x in between all of the x's. Now I need to actually discretize my equation. So my equation is continuous. But I know that this equation is valid at every point of the rod. Therefore, it's valid at point x1, at point x2, at point x3, and point x4. Okay. So let's actually look at that. So I'm just going to remind myself that I have a rod. It's like a line, x0, x1, x2, x3, x4, and x5. And I'm looking for T1, T2, T3, T4. I do have T5, which is 200 Celsius, and T0, which is 40. Those are my boundary conditions. Favorite thing that messes up every differential equation is boundary conditions. Or not having them, or having them so they're complicated and so forth. So boundary conditions really constrain differential equations in a big way. Now, what am I going to do? All I know is that at each and every of these points, my d squared t dx squared plus h times ta minus t is equal to 0. So I need to figure out how to express this in terms of the values at neighboring points, because I'm looking for those values, right? And this is where our so-called finite difference formulas come in. Do you remember vaguely from errors what I said was a finite difference? So if I was looking for a single derivative, just like a derivative at a point, let's say t2, I could take, for instance, a value at t3 minus t2 and divide by this difference delta x. That could be an approximation of my derivative. That's one way to approximate. Another way would be to do t2 minus t1 divided by also delta x, or even t3 minus t1 divided by 2 delta x. Do we remember those? So those are finite difference formulas for approximation of derivatives. Well, it turns out that this can be always approximated. The second order derivative, I can just apply it twice, really. And I will just give you the formula. So it's approximately t of x plus delta x, any delta x, so also this one that I'm taking here, minus 2t at x plus t of x minus delta x divided by delta x squared. This is so-called central difference. For d squared t dx squared. Okay, so now I'm going to do that. At each of these points, t1, t2, t3, t4, I'm going to apply this and see what I get. So if I apply it at this point here, okay, I will get that my finite difference is T1 evaluated, or this temperature evaluated at T x1 plus delta x, which is my x2, right? So I'm going to write it as T of x1 plus delta x minus 2t of x1 plus t of x1 minus delta x divided by delta x squared plus h times TA minus t of x1, which is t1, is equal to 0. Does everybody see this? Because if not, we can't move forward. So instead of d squared t dx squared, I'm applying a discretized formula. That discretized formula grabs values around me, delta x ahead and delta x behind, and my value, and gives me an approximation of the second order derivative, right? So if I apply that formula, and it's valid for any x and any delta x, so now I'm specializing it for that location x1. Okay? At that location, t of x1 plus delta x minus t of x1 plus t of x1 minus delta x divided by delta x squared, and plus that second term is h times ta minus t of x1 is equal to 0. Everybody good? So I applied discretized equation at this first location x1. Okay. Guess what? I'm going to do that for all four. And that's going to give me equations. Now, how is that helping? It's helping because what is t of x1? What is t of x1 in terms of this rod up there? T1. So this is T1. Okay. What is T of x1 plus delta x? X1 plus delta x is x2. So T of x2, T of this is T2. Everybody sees that? And T of x1 minus delta x is T of x0, which is actually my boundary conditions. It's 40. So this is T0. TA I have, that's 20. I have this value, I have delta x. The rest I have. So this equation is equation in terms of T1, T2 unknowns, and everything else is known. And it's a linear equation in T1 and T2. So it's one of my linear equations. And I'm going to get 3 more. Do you see where we're going? At the end, we're going to have 4 equations we're going to solve. For T1, T2, T3, T4. And once we do, we have the temperature distribution we were looking for these 4 discrete points. If I wanted to solve this at a much nicer, finer, not just every 2 meters, but a little better, then yes, I would solve it with smaller delta x, and then I would just have a bigger system. It wouldn't be 4 by 4, it would be, well, 40 by 40 if I wanted it to. Does everybody see? Okay. So that's how we discretize differential equations very often. And we end up with the linear system at the end that we need to solve. So every differential equation solver needs to know how to solve linear systems, which is our basis in our course here. Okay? And at the foundation of a lot of problems, you end up with solving a linear system. So it's really an important problem to solve. Okay, let's get back to it. Let's clean it up a little. So I'm going to multiply with delta x squared. So I'm going to have T2 minus 2T1 plus T0, which is 40. So I'm just going to write 40, plus H, which is 0.01, times TA, which is 20, minus T1 is equal to 0. So I have minus 2 minus 0.01 T1 plus T2 is equal to, on the other side, 20 to this minus 40.2. So that's my first equation. Then we're going to just get the second, third, and fourth, and we're going to solve the system. Yes?
Delta x squared.
Oh, I need to multiply times delta x squared. That's 4. So 4 and 8. There we go. Thank you. All right. See you on Monday.